Hello, this is Bill Johnson at the University of Utah Department of Geology and Geophysics. I'm going to talk to you about our particle surface interaction and trajectory simulation software called Parti-Suite. This was developed by students in my research group, as well as it was ported to MATLAB by Dr. Eddie Pazmiño at the Escuela Politécnica in Quito, Ecuador. And so to get this software, simply go to the web, search under WP Johnson Research Group. That'll bring you to this website. You can click on Parti-Suite software. And what you'll see is that there's a series of executables. This is always changing and upgrading. But the one I'm going to focus on today is the MATLAB executable for trajectory simulation. Once you download that, you can go to the installed software. It will go onto your C drive on the program files under WP Johnson Research Group. And you can then execute it by right-clicking and running as an administrator. And if you don't do that, it won't function. So make sure you right-click and run as an administrator. Once you do that, it'll open a command window in MATLAB. That is not very interesting to look at, but it will, after a couple minutes, open up the GUI. And here's the GUI here. So the GUI is a little bit intimidating to begin with, but it's very, very useful. It interfaces basically with a extended DLVO simulation package we have that utilizes the same parameters. So you can look at the interaction profiles and then look at how those profiles impact the transport. So it's got all of this input, the number of colloids that you want to perform in simulations for at a given time, the conditions for which particles arrest at the surface, either by perfect sync or by contact mode. We recommend contact. You can run this in single or parallel format, but of course running it in parallel format depends on your capabilities, and we can assist you with that, but on your own just single core computer it would be run in single mode. And output parameters, basically you can have larger number of translations occur between outputs through the output interval factor. We're doing every 250 in this case, and you can output a maximum array length so that you don't end up generating files larger than you want to. There are plots that inform you while this is running, so you can either enable them, which are kind of dashboard plots that show you in a gross way what's happening in terms of the particle trajectory, and then detailed plots that show you the near surface and contact characteristics. And you can disable these, uncheck these in order to make the simulations run faster. But a powerful aspect of this GUI is showing you what's happening. So I suggest until you get tired of looking at these, have these on. So the basic physical parameters include flow, so the superficial velocity entering the haplosphere and cell, the injection radius, which is less than the projected radius of the Happel collector because for computational simplicity, and we explain this more in another part of this video or subsequent videos regarding quantification of the collector efficiency. The Happel porosity represents the porous media porosity, but it's represented here as the thickness of the Happel shell, the fluid shell surrounding the grain, and a given grain radius that you input. The total simulation time is a parameter that allows you to terminate the simulation after a certain amount of time if you wish to. It's kind of a gap stop parameter. We don't use it much because we can control the simulation in other ways that I described below. So you have the colloid radius, the colloid density, the fluid viscosity, the relative permittivity, and the temperature. All those are self-explanatory. We have heterogeneity parameters that I won't go into now, but we'll talk about further down in this video. The van der Waals force parameters include the combined Hamaker constant for the colloid interacting with the collector across a fluid. The default parameters all here are for polystyrene latex microspheres interacting with glass across water. And so there's a decay length that goes with that. The van der Waals mode defines whether or not you have a layered system. We're using non-layered surfaces here. We'll talk about layered surfaces in a subsequent video, but it interfaces with the XDLVO profiles that are also capable of taking on layered properties. Roughness, likewise, I won't go into here, but roughness affects both the hydrodynamics and the colloid collector interactions, and so you can run that in smooth mode or in one or other surface, or both surfaces being rough. And so you would define that slip length and define the asperity height, controlling colloid surface interactions. Okay. The van der Waals force parameters for coded systems are given here. We're going to have a version of this soon where these are grayed out until you specify a layered system. So we're going to ignore those for now. Lewis acid base and steric hydration force parameters are given here. And so there's an acid base energy, an acid base decay length, steric energy, and a steric decay length. Deformation parameters control particle deformation on contact with the surface and inform the arrest of the colloid. So there's a combined elastic modulus, work of adhesion, and a contact radius that comes out of those parameters. This again interfaces with the XDLVO simulation software. And so you can calculate these things from fundamental parameters using the XDLVO that we'll describe in another video. Diffusion and gravity forces, multiplier diffusion force corrects the force-based diffusion to match the expectations from mean displacement from Stokes-Einstein equations. And so we found that a factor of, or a 35% positive correction makes that match occur. The multiplier of the gravity force allows you to run the simulations either in concurrent mode, where gravity is in the same direction as flow, which is the case here, or you can put a minus in front of that and run them countercurrent against one another. Then the simulation time step and slow motion parameters are numerics. They're basically multipliers on the primary time step, which is the momentum relaxation time of the colloid. That is scaled to the colloid size, really the colloid mass. And it reflects the time interval over which correlated motion occurs within Brownian motion. So while Brownian motion is random, at smaller time steps, there is correlated motion within that random motion, and that time step is characteristic of the particle and scales with its size. And so to honor Brownian motion, the time steps must be much larger than that momentum relaxation time, and that's what these multipliers are doing. So these multipliers should be greater than 1 for the bulk time step and a near surface time step where Brownian motion is operative. In contact with the surface, we neglect Brownian motion, and so those time steps can be much smaller. The other two numeric parameters are a near surface displacement factor and a contact displacement factor. And what those do is if the colloid is either moving very slowly in the near surface or very slowly rolling across the surface, you may not want to watch it do that forever. You may want to consider it arrested. And so these factors are the fraction of the displacement that you would expect just from diffusion in the bulk fluid. And say that if you're within some fraction of that bulk fluid displacement by diffusion, then you're considering it arrested. Okay, and so that's why these values are less than 1. So up here in this box, we have the mean field potentials for electric double layer interactions. And so we set the ionic strength, the electrolyte valence, and we have the zeta potentials of the colloid and collector, which are the mean field surfaces that one would actually measure using, a zeta meter. And so from their electrophoretic mobilities. And so that is the zeta potential would be calculated from the electrophoretic mobilities. And so they do not account for heterogeneity on the surface, but reflect the mean field values that you would put into mean field DLVO theory, for example. So you can specify where the input parameters are being saved, the name of that file, and the directory to which the values that you input, as well as any output, all the output files would be saved. And that can be done here. And so the typical way that you run the program is you populate all these fields, you run a loading simulation under the conditions you populated. If you've already run those simulations, you can load those parameters directly from a saved file, and that's done with this button. Once the simulation is complete, you can also perform detachment simulations using the so-called perturbation mode, and first load the save file from loading mode, and then you run the perturbation simulation. So we'll show you all that subsequent in the video.